Let's get started. First thing is first. First thing, I'm going to back up a page on my whiteboard before we get into that, and let's do a review really quickly. So let me get my Q&A box out here so I can Q&A you all. Clear this. Okay, so what does the scale show? The elevator that this person is in, he's in an elevator, in case you didn't know, has just started accelerating. It's just started going up. I've told you this guy's mass and his weight, and I told you the acceleration. He starts to accelerate at 0.47 feet per second squared. What does the scale show? I'm going to give you guys 30 seconds or so to see if anybody can get an answer in the Q&A box. Ready, set, go. Yeah, what does the scale? Nice, Spence. I see that it's a joke. All right, here's the here is your hint. The scale is showing the normal force. Scale is showing the normal force, and you all should be thinking, what needs to go into the sum of the forces? Okay, I got a few correct answers rolling in here. Ten seconds. Okay, good job to Brandon, Megan, Jared, Caroline, Smith, excellent work. Landon for a good guess. I think we'll see that guess. Jackson for a good guess also, and Drew sneaking in at the end with the correct answer. Excellent work. Okay, let me get back to my chat box here. Let's work this really quickly. So the elevator problem, we just need to consider what are the forces at play here. We have this person's weight, which is going down, and we have the normal force of the scale on this person going up. So these guys are going to be opposite one another. So we'll have the normal force. We'll have the normal force minus the weight will be equal to mass times acceleration. Of course, when the acceleration is 0, this person will be in equilibrium, and this side of the equation will be 0. But right now, that's not the case. We have the normal force, we have this person's weight at 128 pounds, we have an acceleration for slugs, and we have an acceleration of 0.47. So basically 0.47, what is that? 1 point something? 4 times 0.47, 1.88. And we're just going to add 128 to both sides of the equation. Add 128. Add 128 to both sides. We get 129.88 pounds. We find that is equal to the normal force. Kapow! That is the correct answer. Good work. Any questions on this, on the elevator problems? If you didn't remember this setup, or you didn't figure this setup out, with the normal force going up, the weight going down, then it would probably be pretty tough to solve this problem. But this is typical equilibrium versus non-equilibrium problem. And it's also, for some reason, is a favorite problem on standardized tests like the GRE and especially the MCAT, which is the Medical College Admissions Test. If you want to be a doctor, you got to take this big test, and they just love these elevator problems. You're welcome. On your own 6.3. Let's let's rush through this. This was the most difficult one, and the reason this problem was difficult is because of how it was framed. It said, how heavy can this fish be? Asked this problem. What is the weight of this fish if this string right here, if the tension on this string, which we will call T2, can only sustain 13 pounds of tension. And so it becomes a little tricky because you're thinking, okay, hold on. I don't know what T1 is. I don't know what the weight is. And I mean, I know the maximum amount of that T2 can hold, but do I even know what that is? And so you start thinking, well, hold on, I seem to have all these unknowns. What the heck am I going to do with this? How could I possibly solve this? And what you need to do is you simply need to say, okay, I'm going to assume that the tension in this string here, that T2, is equal to 13 pounds. Tension is 13 pounds in T2, and in T1, T1 is what we're solving for. The tension in this string is 13 pounds. And also something we're solving for is the weight. So we're just assuming that the tension is 13 pounds, and then we'll solve for the weight, what the weight will be at that tension. Is this making sense, everybody? Yes, no, probably. So the question really is, what maxes out? What weight, what W maxes out, and what is the what totally stresses out this string here? What maxes out T2? And to solve for this, you set up all the x and y components of each of these tensions, and we can do that. And I'll try and do this as quickly as possible. So I know that T2 is equal to 13 pounds, but let me start splitting things up into their x and y components. So T1 sub x is equal to T1 cosine of 40 degrees. T1 sub y is equal to T1 sine of 40 degrees. T2 sub x, T2 sub y. This one, the x component is equal to T2 cosine of 180. And we know what T2 is, actually, so we can just say, hey, it's negative 13 pounds. Since T2 is 13 pounds, there we go. This cosine of 180 is negative 1. T2 sine of 180 is equal to 0. Good. Are we done? Not quite. We have the weight to deal with. The weight has no x dimension. Why is that? Because the weight times the cosine of 270 will be equal to 0. Kind of nice. And the weight, its y dimension, will be the weight times the sine, excuse that messy sine symbol, will be equal to the negative weight. So even on the this is a great exercise to do. Even on the numbers that I know will be 0, like the sine of this string or the cosine of the weight, I still write them out and say that they're 0 just to keep track, just to be complete. A little more work I need to do here. Can do some math. The cosine of 40 is 0.766 T1. The sine of 40 is 0.643 T1. How do I know it equals 0? Excuse me. I know that I guess my calculator tells me. So it's Yeah, why does it equal negative? Yeah, for both of these situations, if you know, you will just find, if you enter in your calculator, what is the sine of 270? If you find the sine of 270, which is what this weight is, the sine of 270 is -1. So the zeros and then the negative down here, and also the negative up here, that these are functions of these are just the trigonometric functions working themselves out. Does that make sense? So all of these functions right here, cosine of 180, sine of 180, cosine of 270, sine of 270, those are the straight lines, the lines that are not at an angle to the left. Why is it w instead of -1? Yeah, because I'm searching for the w. So the w is the variable or the unknown that I'm trying to solve for which I'm trying to solve for. It's right here. W. I'm trying to find the x and y dimensions of the weight, and ultimately the weight is what I'm trying to solve for in the problem. But I'm trying to split the weight up into its x and y components, but really it's just a y component, right? It's a y component down at 270 degrees, and so just keeping that 270 degrees in mind will give me -w. So I'm still looking at Spence's question, why is it w instead of -1? Well, it is -1. But it's w times -1. Let me write that out. We have w times the sine of 270, which is -1. And just so happens that the cosine of 270, if you enter that into your calculator, 270 cosine, you get a big fat 0. Something similar is true for the 180. The cosine of 180 is -1. So it's t2 times -1. Now we happen to know what t2 is, the value, so we plug that straight in. But the sine of 180 is also 0. It's 0, just like the cosine of 270. Right, yep. The cosine of 270 is 0, the sine of 180 is 0, and the flip side of that is these guys are -1. Absolutely right. Yep, these functions. You kind of get to know these functions a little bit, and also that's what you'd expect, right? I mean, does this 180 degrees, does that have a y component? No. It's purely in the x direction. It's pure run and it's no rise. So if the sine is the function that seeks to reveal the y component of something. Well, this has no y component. At 180 degrees, there is no y component. It's all x component, and that's why it's 0. It is 100% x component, which is why the cosine of 180 displays -1, like 1, which is kind of like saying 100%. It's 100% x component. Okay, is that all explained? Good. Now we go to looking at the sum of the forces in the x direction and the sum of the forces in the y direction. And this will give us two equations that we can use to solve for these two variables, t1 and w. The sum of the forces in the x direction, let's look at them. We got 0.766 t1. That looks good. Oh, one more thing. This is really important. It's an equilibrium, right? So we know that the sum of the forces for each of these are going to be equal to 0. Okay, let's start adding this up. T1x. So I'm looking down here. I'm pulling all the x things, all of the x forces. 0.766. That's T1. And then we have another x force down here, -13 pounds, -13 pounds, and then the final one is just 0, so I'm going to say +0 just to keep track, and that's all equal to 0. Nice. Those zeros will make it easy for me to figure this out. Okay, I have this entire equation and only one unknown, which is nice. I can just solve for it immediately. Solving for T1, doing some algebra, gets me set up like this. T1 is equal to 17 pounds. That will come in handy. Let's turn to the y dimension. I have 0.643 T1. That's part of my y forceage, one of my y forces. 643 T1. And in the y direction, we have 0 plus 0. And the weight is negative weight, so minus W is equal to 0. If I rearrange this, I'll find that the weight is equal to, I'm skipping a few algebra steps here. I find that the weight is equal to, so I'm putting the weight on one side of the equation, it's equal to 0.643 T1. And finally, if I put this T1, this value I calculated, into this spot over here, I get this. So I'm combining these equations here. Saying, hey, let's put that over there. Let's put this T1, 17 pounds, into the T1 spot over here, which gives me a weight equal to 10.9 pounds. Okay, how's that look? Good, good. Any questions so far? If not, let's move on. If I understand it right, I've only got about 12 minutes left of class. So be it. Let's see what we can cover. Thank you to all of you who worked that problem all right, and we're just looking at a review. I appreciate your attention. Good work. Let's move on and talk about rotational motion. Okay, here's the situation I want to present to you. Let's say that there is a nut, and you're trying to loosen this nut with a wrench. Once again, a few terms. What is this called right here? The point that around which the nut will rotate and around which the wrench will rotate also. What is this called? Let me call on somebody here. Actually, anybody can answer if you're quickly, but I do want Catherine Collier and Drew Darty to answer if you happen to know. What is the term for this right here? This little dot around which things will rotate. Do you happen to know? Yes, it is called the axis. I like that. More specifically, it is called the axis of rotation. Sorry, Drew. Oh, there, Drew got it in pretty quickly also. I love it. Axis, very good. Axis of rotation right there. Okay, so here's the question. Let's say that I come along and I apply just a little bit of force. I grab onto the wrench and I pull on it with 10 newtons. What happens if I pull on it right here? Well, if 10 newtons is sufficient, if this bolt is not very stiff, it might work. It might start to turn. What about if I apply 10 newtons, the exact same force, but I apply it over here? So I'm grabbing onto this and pulling down. How about that? How about if I grab the wrench at the very end and apply 10 newtons? So which of these will have the greatest effect? Which of these forces will be the strongest force? Now, of course, they're all the same force. It's all 10 newtons, but which of these will have the greatest effect? And let's have a number of people. Anybody can type in an answer if you'd like. A, B, or C? Will force A have the greatest effect, B or C? Good. Spence is on top of it. Good. Jackson, Dean, Jared. C it is. Why is that? Why is it that C has the greatest effect? It's mysterious. If you push down over here, you get more. Yeah, Jackson Dean is right. Leverage. Leverage is correct. If we draw an imaginary line, the acceleration, straight out, we can measure the distance from the point that the force is applying itself to the axis of rotation. And the greater that distance is, the greater the effect of the force. We call this leverage or the lever arm. The lever arm, and I may have messed this up at the end of last class. Sorry about that. But this is we call the lever arm. The longer the lever arm, the more effect it has. Now, this is the fact that force C has a greater effect is an example of the concept of torque. Here we go. Torque, and I've spelled torque. The T that I've written here, I purposefully made that look kind of funny because the equation for torque, we like to use the Greek letter tau. T-A-U, tau, which is really pronounced tav for all of you Greek scholars, all of you seniors in high school taking Greek. I never did. I always took Latin, took advanced Latin. More of a Latin guy myself, but hey, Greek is pretty important. Tau is equal to, the torque is equal to the force that is perpendicular, to the lever arm. You notice that I kindly drew all of these forces so that they were at right angles with the lever arm. Nice of me, huh? The force that is perpendicular to the lever arm times the lever arm. So multiplied by the lever arm. And we are gonna call the lever arm R. Why do you think we call the lever arm R? What is this? What could that possibly stand for? So here's my question. Why is this lever arm called R? Who knows? Why is the lever arm called R? It's just, what it represents is this distance. And we got two good guesses here: rotation and radius. Not a bad idea. The distance from rotation. That's not a bad guess, Brandon. But and it might be correct because I'm guessing on this also. But I think it's radius. I like radius. And radius, the idea is the distance from the edge of a circle to the center of the circle, of course. So, and since this is going to be moving in a circle, radius works well. So this is your equation, and I'm going to give you the definition, but the definition is really just a statement of the equation. The definition of torque is the tendency of a force to cause rotational acceleration, period. Here's your definition of torque: the tendency of a force to cause rotational acceleration. So let's solve a really quick torque problem. Let's see here. Let's say that I approach this wrench that I have drawn here, and I decide to apply 70 newtons. Here we go, 70 newtons of force on this wrench. And the wrench is exactly 140 centimeters long, which is pretty long. Not bad, which is 0.414 meters. What kind of torque will I get out of this thing? What kind of torque? So let's solve for it. Torque is equal to force perpendicular to the lever arm times lever arm. Torque is equal to 70 newtons times 0.14. Nothing very mysterious about this. Multiply them together, get, and what do you know, 9.8. Just a coincidence that I got this. 9.8. And what do you think the units to this are? It's not just newtons, by the way. Torque is not just newtons. 9.8. 9.8 what? It's 9.8 Newton meters. 9.8 Newton meters. That's the unit. Not very creative, is it? Kind of wish they came up with something else. It's but a force times a distance actually is work. And so I think later on we'll discover that the Newton meter is really a joule. But for now, when representing torque, torque is a little bit different. Since it's rotational motion, we really can't say it's a joule. And what's a joule anyway? Forget about that. We'll learn that later. For torque, the units are Newton meters, and that's what we'll go with. Okay, I think I have enough time actually to go through one more example to get you guys' minds a turning. Okay, so let's say a plumber has two different wrenches, and I'm not going to draw them. You're just going to have to use your imaginations. One wrench is 15.2 centimeters. The other wrench is 30.5 centimeters. Okay, so one's a lot longer, one's heavier duty. This plumber, we're still dealing with wrenches and things, right? It's kind of nice. This plumber has a maximum strength. The maximum force he can apply is 653 newtons. So which wrench is going to be able to give him the greater torque? Obviously, we know that this longer one is going to give him the greater torque, right? It's longer. He's got more leverage. He's got a longer lever arm. But how much more? Not too hard to figure out. Let's calculate these two torques, torque 1, torque 2. Convert these into meters. Times, I'm kind of switching things around. Usually I write the force first, but whatever. I'll write the lever arm first, 0.305, 653. This is an example to compare different torques. First one's 99.3 newtons, and the second one is 199 199 newtons. We'll go with that. And they're not just newtons, sorry, they're Newton meters. Newton meters, there you go. Yes. Brief but simple example. Tomorrow we'll talk about rotational equilibrium. I'll turn it over to your teachers to dismiss you. Thank you for your attention. Have a good time at your chapel thing. Bye-bye, everybody. Nice to see you.